a little bit. So basically, I'm posting everything on your Canva site, as you can see. And today I'll post the lecture and also the video. So now let's go to the lecture itself, and let's start from here, from the beginning. So binding energy. So as everyone knows, this famous equation by Albert Einstein, E = mc squared, which he wrote down as a footnote in one of his famous papers. He didn't even think it was so important, but this is the energy release by any nuclear reaction, a nuclear weapon, everything where there's a mass difference. Instead of m here, it should be like delta m, the change in mass between whatever you have before and after, provides this energy. So now we are going to explore a little bit more, and I want you to be aware of the scales we are talking here. We are talking about scales of if this is an atom, let's say it's a gold atom, and we put it at the same size as the sun. The sun, the outermost planet, which is Pluto at that time, and now people don't consider Pluto as a planet, but I don't care what Pluto, which is very, very far away in our solar system, is just only 1.6 miles, right? If you compare with an atom, the electrons are about 3.3 miles, about 2 times farther away the electron is from the nucleus than the farther planet is from our sun. So this is telling you the huge scale. It's telling you that most solids that we see are in fact empty space. Your table. Your table. You can knock on your table, and obviously your hand is you're going to hurt your knuckles if you hit very, very strongly. But in truly, this is electrostatic repulsion. What is happening between your hand and the table? This reaction here is electrostatic interaction between the two surfaces of your hand and of the table, but in truly, most of the space is empty, because as you can see, any atom, there's a nucleus in the middle. Like I say here, is the head of a needle in the center of a football pitch, right? So this is what we see, and it's difficult to believe, but this is the situation. So now I want to go a little bit more and understand that the nuclear radius is given by this formula. I want you to remember this formula here, where R0 is equal to 1.2 10 to the minus 15. Actually, I should mention here Fermi. And actually, I should write it down here, so we don't, when we put it in the let me see here. Let me remove this fellow from here, otherwise we don't see. Let me put this one here as this one. Here we go. All right. So this is the radius of a nucleus is 1.2 times the mass number, which, as you know, the mass number is A equal N number of neutrons plus number of protons. So if you have a nucleus like oxygen 16, you will have to multiply 1.2 10 to the minus 15 femtometers. This is a Fermi, which is 10 to the minus 15 meters, right? 1 Fermi is equal to 1 femtometer. 1 femtometer actually 10 minus 15 meters. So this is 1.2 10 to the minus 15. So that's already in femtometer given. So so okay, so what I wanted to say here is that the radius of a nucleus is of a few Fermi, and then here yeah, we are already multiplying by 10 to the minus 15. But basically, you have 1.2, and whatever is the say we want to calculate the radius of oxygen 16. So we just have the 1.2 times 16 to the 1/3, and that will give us 3 Fermi, right? So R naught is true, but you don't need to write the is 1.2 10 to the minus 15 Fermi, but this is already given in Fermi, so you don't need to put the 10 to the minus 15, basically. Sorry, that's very silly. But how do we get this a to the 1/3? Is because the number of nucleons per unit volume is roughly constant throughout the volume. We have the same number, the same density. So basically, A, which is the total number of nucleons divided by the radius of the nucleus, is a constant. And this has been proven. As you can see, this is the graph of the square mean radius over A or to the 1/3. And you can see that there's a constant line here, which agrees with the radius being proportional to A to the 1/3. And this assumption here, which is also based on experimental data. So I posted different references here. So Theoretical Nuclear Physics it's an old book, but it's nice displaying pages 14 and 16. You can find all these books in the library. There are 3 copies, I think, of Rowe and Wood. Obviously, Crane is also a very nice is the book that we are referring to, but you see there are other chapter 1 on fundamentals of nuclear models by Rowe and Wood is also very interesting. And this book, Theoretical Nuclear Physics by Blatt and Weisskopf, is also a very interesting book. So the introduction, the first chapters are a nice read for everyone. So now I want to ask you one little question. So what is the radius of the nucleus? So if we look at this plot is the cross section versus an alpha particle. This is basically, let's say, the Rutherford cross section that hopefully you saw in modern physics. Rutherford cross section is given in classical mechanics. So actually, remember, I want you to remember what is Rutherford cross section. And we're going to go through a little bit of I want to explain one thing. If we do this, I'm going to change this color to black. I'm going to make it here. And I'm going to bring this right there. Okay, so if the nucleus follows a classical trajectory, a classical physics, and there's no nuclear excitation being involved, these are the dashed lines. The dashed lines indicate that as the alpha particle, imagine we have an alpha particle like we have with Rutherford's experiment. Remember, we have a Rutherford experiment. Hopefully, I think we have it here from yesterday. Here. Remember, in Rutherford's experiment, we have the alpha particle coming through, and we have the gold foil. So here we have the same kind of thing. The same kind of thing. I'm going to put this one here for you to remember. However, let's do it here small for you to remember the picture. However, here instead of gold, we have tantalum and silver. These are the symbols for tantalum, and this Ag, as you know from the periodic table, this is the symbol for silver. So now, if we bombard these alpha particles, we have an accelerator rather than an alpha source, and we have here a radioactive source. But if we have an accelerator, the situation change. So we can always increase the alpha particle energy. So we have an accelerator and we can increase the energy of this alpha particle. And instead of changing, we can also get the radius of gold for this particular case. But here are the plots for silver and tantalum. So instead of having gold here, we have, imagine that we have silver, a thin layer of silver, and we see that this follows a classical trajectory, a classical cross-section given by Rutherford through the dashed lines, right? However, at some point, at some energy, the situation change, and the data points, as you increase the alpha particle energy, the data points come down suddenly and do not follow this Rutherford cross-section anymore. Is that clear, guys?
Sorry, sir, can you please explain it again? I didn't get it.
All right, okay. So in any, so we have, let me see whether we can explain this better. So we have an alpha beam. We have an accelerator, and we have an alpha beam, a helium-4 nucleus, being accelerated at different energies, 10, 15, 20, all these data points corresponds to different energies. And this is how much they scatter at these particular energies. So they scatter, and they lose. As you increase the energy, you get less counts. Basically, this is proportional to the number of counts, number of scatters. So this is the y-axis, and this is the x-axis. So as I say, these follow a particular trend, and these also follow a particular trend, but up to some point. Up to some point, this Rutherford scattering, this basically classical scattering, following the Rutherford cross-section, where just solely electromagnetic interaction is playing a role. So the alpha and the target, the beam in any classical trajectory, it will follow a hyperbolic trajectory because of the Coulomb force. So basically, this is what is happening in the classical world, right? When we don't involve any nuclear force. However, and this is what I want you to see, that at some point the nuclear force is playing a role. So once you touch the nucleus, then suddenly there's a drop, and the curve doesn't follow the classical trajectory anymore. So it's not classical, it's not just Coulomb excitation, Coulomb scattering, Coulomb interaction, but there's some nuclear effect as the silver and the alpha come together. So this is a problem for us to determine what is the radius of silver and tantalum. Knowing actually, let's write it down here, knowing the radius of the alpha particle. We know, I'm going to write it here, radius of alpha particle. We need to know this. I'm going to give you this as a given. This is 1.2 times, let's call it here, times 4 to the 1/3. And this give us equal, let's put it down, everything in the same color. So everything is clear. So radius of the alpha particle is equal to 1.2 times 4 to the 1/3, and that's equal 1.9. Right, we assume that this is 1.9 Fermi. 1.9. is the radius of the alpha source. So see this, I give you this as a given, but we're not going to use the same trick for the silver or for the tantalum. Let's make this a little bit smaller so we know. All right. This is going to be our given. And now we are going to apply conservation of energy to determine the size of the nucleus. What's the radius or size of the nucleus? Okay. I'm going to put this one here so it doesn't bother us. So we just want to remember this because we have, instead of an alpha source where gammas are emitted a particular energy, we have an accelerator so we can change the energy of the alpha particles. So the key question is here. When there's a deviation from the classical situation here, and we are going to apply, let me show you what I want to do. Yeah, let's go here. I'm going to go here. So this, let me just open this thing. All right. So this is the problem I want to illustrate. I think in this way it's going to look better. So we have a helium 4 or an alpha particle, as I say, and we accelerate it at different energies, different kinetic energies, which we're going to call T lab. And this one is the one given by these energies here on the x-axis, right? Then let's say assume this is let's make it 17. These 3 data points here, 17. Let's say, right? 15, 16, 17. Maybe we can make a straight line to make it sure. We can make a straight line here, and we can move it and say, okay, I want to move this, and this is about that. About 16. Let's say 16. That is a straight line at 16, and that's where the deviation happens, right? That's where the deviation happens. So we have 16 MeV. Where the deviation is happening. So before, this guy was following a typical Rutherford trajectory, hyperbolic trajectory, but suddenly this trajectory changed, as we can see from the typical cross section. Sorry, right here. Suddenly this follows this hyperbolic trajectory, but suddenly at 16 MeV, something changed. Right? So something changed, and this gives us the hint of that the two guys are touching each other. So there's an ingredient which we haven't explored yet, and this is the range of the nuclear force. So tomorrow we will learn from quantum mechanics what is the range of the nuclear force, but so far I want to tell you that the range of the nuclear force is very, very narrow. So let's say that the range of the nuclear force, sorry. Yeah, we need to know this, and we need to know the range of the nuclear force. Let's call it delta X is equal, say, to 1.5 Fermi. So let's make it, yeah. Let's call it 1.5 Fermi. So if these two guys, they get close to each other, basically, let's zoom in here. We have the silver, and we have the alpha particle here. So if these guys, they get together by, let's call it delta X, we're going to calculate this tomorrow. Let's say 1.5 Fermi for the time being. then the nuclear force awakes. So we have nuclear force happening at this range. So the two particles and the two nucleus, they get close by 1.5 Fermi. Very short range. Above 1.5, about 3, 4 Fermi, let's assume that above this range, this distance, there's no nuclear force. And we're going to make that approximation. Sorry, I have to go down. So this is the range of the nuclear force, we assume. We're going to give the symbol, which is going to be delta. And this is the range of the nuclear force. Okay. So these are the two ingredients that we need to solve this problem. And now, with that, we are going to apply conservation of, actually you're going to do it. You're going to apply conservation of energy in the center of mass frame. So in the center of mass frame, we have 1/2 of mu u1 squared. This is the kinetic energy in the center of mass, is equal to the potential energy in the center of mass, which, as you know, is Z1, Z2, E squared over R, right? This is the potential. So basically, we are going to assume that this is the closest approach of the nucleus, where now we are, the nuclear force is being ignited, is being waking up, right? It's VUCA. VUCA, the nuclear force is waking up at this range. At this range, let's call it B. Let's call it R, doesn't matter, whatever is R. So basically, what we want to deduce is what is R for this to happen. So R will be the distance between the two centers. Okay. And the distance between the two centers, let's call it R, it will be equal to the radius of the alpha, or the helium-4, plus the radius of the silver, which is what we want to calculate, plus this delta X, which we call it 1.5, is 2, 1.5 or 2. We'll see this later on when we solve the uncertainty principle. But let's assume for the time being that is 1.5 Fermi. All right. So now with those ingredients, we can determine what is the mu. Actually, mu is the, let's make everything from scratch. Close. Let's open a new one. So let's do it from scratch. So we have these guys and this guy, and we have the distance between the two centers, as we say, is equal to R, right? But these are, we have the radius here of the silver. Inside here, we have the radius of the alpha, or the helium-4, and this here is delta X, right? From here to here. We assume that delta X is equal to 1.4 or 1.5 Fermi. And then we assume that R alpha is given by, as I mentioned before, by 1.9 Fermi. Where for this one, we have assumed that this is equal to 1.2 times a to the 1/3 Fermi. And now we apply conservation of energy in the center of mass frame. T center of mass is equal to V center of mass. And T center of mass is 1/2 of mu initial velocity squared. And mu is the reduced mass, which is m1, m2 over m1 plus m2. And this is equal to Z1, Z2, E squared over R. Where E squared, I'm going to give you another hint, is 1.44 MeV Fermi. Right. So this is reduced mass. You can Google it, or reduced mass, which simplify the two-body problem, because now we have one mass, and this is one of those simplifications which is very good to use in classical mechanics. So from here we are going to deduce what is R, but we need to know what is U initial. So U initial is T lab, now it's in the lab frame, which is equal to 1/2 of the mass of, in this case, the alpha times in U initial square, right? This is the velocity square. So T lab is given by that point. What we say before is 16.
Sorry, sir. What does T lab? What does T lab represent?
T lab, yeah, T lab is the energy of the alphas. This is T lab, alpha particle energy. Okay. This is the kinetic energy of the alpha particle is given by this. Is basically the accelerated the energy of the alpha particle once it's accelerated. Okay.
Okay.
So now the mass of the alpha. The mass of the alpha, we need to deduce what is the mass of the alpha. And so we know T lab, as I say, we are going to, again, I go to the same place, I want to go down. So T lab, we say is around 60 MeV here for the silver nucleus. So T lab is 16 MeV. And this is 16 MeV. So then obviously U1 square is equal to 2 times 16 MeV. Let's keep the mass, the units for the time being, over the mass of the alpha. And this is one of the exercises I wanted you to do today, is to determine what is the mass of the alpha in MeV. So this is another exercise, but this is the remaining. The remaining is almost done. So once we have, I'm going to leave the problem here. Once you have U1, I'm going to now determine the mass of the alpha. But once you're going to go back here yourself, I want you to solve this problem and send it to me. Okay. So I give you all the questions are here. And this hint here, that this is the R, is the whole thing. So you're just going to get the radius of the silver is going to be easy if we assume these two, right? Basically, I'm giving you too much of information here. So now let's go and do something else. Let's calculate the mass of the alpha particle. So here I gave you, you're going to follow this presentation because I gave you before the table. And if we go to the here, we have the masses, right? And here we have the mass of the helium, which has an excess mass of 2424. So I don't. I want you to calculate from the mass excess what is the mass of the alpha particle. I'm going to find minus name and make your own mass excess. Make your own spreadsheet or your Excel file, LibreOffice. I'm going to maybe use any of these. one here. Yeah, and I have here what is the mass number, what is the mass excess. So basically, I can determine any masses, masses that I want. So let's say, and this is the equation, 931,494. 931,494 is actually, everything is in the lecture notes, is one atomic mass unit is 931.494 MeV per C square. So then we are going to determine, so we're going to put here the mass number, which is 4. I don't want that. So we're going to put the mass number here, 4. I'm going to put the mass excess, which is given in kV. So I want to convert this to, I'm going to copy the whole thing. I'm going to convert this to MeV, that's the alpha. So you're going to convert to, copy that number there. I want to put the point here because it's MeV. I'll remove this point here. Right. And this, I'm going to add more. And this is atomic, the mass in atomic mass units. So you can see this is the mass of the alpha particle in atomic mass units. Let me make this bigger. But these are the things that I want you to be able to calculate. So mass excess is very easy to determine. You just go and Google quickly. All these things are in Google very easy and very nicely explained. So mass excess, here we go, in Wikipedia or here, you know. So this is basically the, also in Crane, you see as a reference is given there. So the mass excess, the formula is not here, it's not obvious, but here we go, the mass excess is given here. Oh, that's a PDF. Here we go, we're going to see. But basically everything is in Crane. All the formulas that you need. So what is this now? Let's look at this quickly. The mass of a nucleus, okay. So here we go. This is the binding energy, and we have this also in our lecture. And this is the mass excess. So the mass excess, the tables normally come in this mass excess. So the mass will be of the nucleus will be given by this formula, which I have incorporated here. Basically, this is the same thing. The mass of the nucleus will be C4, which is the mass excess. Let me just write this down, because these decimal points are also very important, because that depends on how much energy released, how much is the binding energy of the particle. So this is the for the alpha particle, and I'm going to copy this in our folder, lecturing quantum mechanics, 2001 lectures. Here we go, for helium. And as you can see, it's just very easy. You get the mass excess divided by 931.494, which are the MeV C squared per atomic mass unit, that, and plus the mass number, 4. And this number is your 4.0026 is the number that we use in our calculation for the mass of the alpha particle. So the mass of the alpha particle is equal to and what is it now? Here, to 4.0026. Generally, you should put the whole number, 4.0026. You put all the numbers. Remember, this is almost 4 because this the helium here, helium 4. And when you run the kinetic energy in the lab frame, which we say 16 MeV, this is equal to 1/2 of 4.002426 whatever U1 square. So now let's see if the units are okay. So it's 2 times 16 is 32 MeV divided by 4.0026 atomic mass units. Atomic mass units that you need to convert, to multiply by 931.494 MeV per C square, which has an atomic mass unit, right? And then this is equal to 32 MeV, and this number here, we can multiply right away. Is this here actually multiply by 931.494 in MeV C square, which is 3728.4, let's call it for the time being, 3728.4. 3728.4, and this is now in MeV per C square. We remove the AMUs here and here, right? And now we can remove this and this. And then we have 32 over, and let's see if that's correct, 32 over 3728. 3728, yeah? So 3728.4, and then this C square goes up. So basically, this is equal to 32 divided by 3728.4, which is 8.592. 8.592, 10 to the minus 3 C square. So we can do the following, the square root, and then we get, but that's what we need actually, right? In the equation that we have here, this is what we needed to determine. So we need to determine U. And let's see. Let's go back to the equation that we needed before, which was let me see. It was actually here. This one here. Here we go. That one, right? So what we need is actually yes, we need this guy square. So we already have it in this equation. Basically, this is times C square. So you can, if you want to, if you are curious enough, you will see that let's see, in terms of C square is equal to this. So if we do the square root of this number, we have how fast this particle, this alpha particle goes. If we do the square root of that particle, is equal to 0.093, basically 9.3% the speed of light. We are accelerating the alpha particle at this energy. Okay, so then you get U1 square once we determine what is the mass, and remember how to get the mass excess. You always get the tabulation always comes in mass excess, as I mentioned here. So you take for any nucleus, you do the same, and you get this in keV. You make it MeV, as we just did here, and from the mass excess we take the mass excess and divide by 931.494 MeV per C square, which has an atomic mass unit, plus the mass number, and you get this mass in atomic mass units, and we can go again and multiply by 931.494, and you get the mass in the right units, MeV C square. Remember, it's the right unit because the energy is equal to mc squared. So the mass, MeV per c squared, right? The c squares will go away for the energy to be given in MeV, right? That's the unit of energy. So in that way, we have calculated the mass, and we can go back here and determine what is the radius of the silver nucleus. So I want you guys to do that now, and finish the problem and do the same thing for the other nucleus that we have here, for the tantalum nucleus. And again, the idea is everything is classical, everything is okay until the nuclear force wakes up. The nuclear force wakes up at that particular range, at 1.5 Fermi, right? So knowing that, we know that once the nuclear force wakes up, there's going to be a deviation from the Rutherford cross-section, because the Rutherford cross-section only involves the electromagnetic interaction. So this sudden change from the trend, nice trend here, but this one is even better. Tantalum trend looks beautifully here, but then suddenly, boom, at a certain point, at this point in particular, the situation changed, right? So at that kinetic energy, and remember, it's very important that this is the kinetic energy I'm saying. This is the kinetic energy in the accelerator. Whenever you go to any laboratory, they give you the kinetic energy in the lab frame, but that kinetic energy in the lab frame has to be converted to, this is the kinetic energy in the center of mass, right? So don't use the kinetic energy in the lab frame here. This is a common mistake. Use the kinetic energy in the center of mass, so you can determine the initial velocity from this formula here, right? Independently. So once you get the initial velocity, you can determine what is r, and once you know what is r, you can determine easily what is the radius of the silver, and we can check with the formula I gave you before. Right here, with this formula for the radius of the silver, you can put the silver, what is the mass number of the silver here, and you can determine with this radius and see whether there's any difference between what you measure here from the Rutherford, from deviations from Rutherford scattering, and what you get with the formula. So we start linking things together. You see, when we work, we want to check if the result makes sense or not. So we think, we make a logical explanation, we do the mathematics, we understand the equations, and once we do that, we compare with whatever was the definition of the radius given before. So this is the lecture that we're going to follow, and maybe the same approach is here. You go here and you want to know what is the binding energy of the nucleus in its ground state. So you go and see how many protons that nucleus has, how many neutrons it has, right? You go again, you go to the tables I gave you here, you get the mass excess, and you prepare your own one. I want you to prepare your own thing here. So not to copy mine, just do your own thing and make sense, you know. So make sense means, for instance, 12 is the mass number of carbon. So we go here and do Control F, 12, space carbon. And you can see 0 here. This is the definition. Mass excess is 0. Let's see. This is the definition of masses. So the atomic mass unit of carbon is exactly 12. Okay. So, but this is the still the mass in MeV per c square. So this is always the number that we want, because we are always using MeV Fermi units in nuclear physics. So basically, you go to the number of protons, multiply by the proton number, which is this one, by the mass of the proton. Then how many neutrons do we have? Multiply by the mass of the neutron. And so on and so forth. You can determine really minus the mass of the nucleus in particular that you want to calculate. So you want to calculate, as I say, in here, I say calculate the binding energies. And these are work to do for you, right? These are assignments. Assignments for you to do. Calculate the binding energies of all these fellows. And using the tables I just gave you right now. So these are the things I want to see. And you're going to provide all this information to the tutor, to Craig. I want everything in one PDF. You finish one, copy all the PDFs together. So basically, I want you to go through another assignment here. Another assignment there is just to study the semi-empirical mass formula. So I'm giving you lots of information. The Q values of the reaction where masses are involved. Masses are very important, and they are very precisely measured, atomic masses, which is quite surprising. But there are assignment here. Assignment there. So there are things I want you to go through this, and we are going to have a little test next week about the information that I'm providing in the first days, right? I know tomorrow you have a quantum mechanics test. So after tomorrow, I will provide more information on this because we haven't gone through this. But I want, for instance, what other information can we learn from the binding energy curve? This is the binding energy curve, and you will have positive energy being released if you fuse elements up to reaching iron 56, so actually nickel 62. And the same thing, you have energy, positive energy being released, and this is part of us learning what is the Q value of the reaction, which comes next. But basically, this is the curve which peaks here around nickel 62, and most of the stars produce elements by fusion, produce energy by fusion up to reaching this point. And after reaching this point, you need to do other kind of reactions. You need to have stellar explosions for this to reach the energies and the amount of neutrons needed to produce heavier elements, all these guys here. But let's focus on the binding energy curve per nucleon, binding energy per nucleon, right? And as you can see, it doesn't matter how many more nucleons we add to the nucleus, how many more protons or neutrons we add to the nucleus. There seems to be a saturation property. Here I'm going to write another line around here, right? There's a kind of saturation property that there's no, you will have masses and you increase the mass number, you increase the kilos, so you always will increase the gravitational force. The more massive is an object, the more gravitational force you have. The more charges you add to an object, the more Coulomb force it will have, right? However, the situation is totally different with nuclei. It's totally different because it doesn't matter how many more particles you add, how many more protons or neutrons you add to the nucleus. It seems like there's a saturation of the nuclear force. We don't have, it doesn't increase anymore. Basically, that's what we really mean. So this property is very important for us to understand how things happen in nuclei. And I have another assignment here, which tells you, it's asking you, looking at the curve and knowing the radius of the nucleus, given by this formula as we know from before. So there's no mistake. Let's remove this thing. You know, it's already in Fermi. So we're going to deduce what is the range of the nuclear force. This is a smart idea that you're going to learn. So for that, before we immerse ourselves into learning about the binding energy curve, binding energy per nucleon. So we're going to learn what is the binding energy per nucleon. We're going to calculate masses. We're going to calculate binding energies. I asked you before to calculate this in particular. Calculate the binding energies of alpha, nickel 62, uranium 238. All right. So then I want you to see how the more particles you add doesn't have any effect in the nuclear force. And finally, I want from this plot, I want you to be able to read graphs. This is a very important tool that you are going to acquire sooner than later, right? We need to know how to read graphs. So this graph will tell us what is the range of the nuclear force. I'll give you a hint. We have already calculated it today during this lecture. So what is the range of the nuclear force by looking at this binding energy per nucleon curve? This is for you to think about. This is an idea that comes after hours of work and trying to understand this binding energy curve. Wow, how the force saturates, or when does it saturate, and when does it not saturate? So these are the questions that you may ask quickly, and we'll explain this next day. But I will ask one of you guys to explain. Actually, not one. I ask everyone. So I want us to come with a conclusion. This is something that you wouldn't find in Google. This is something that where you have to think. And these are questions which I don't think you will find them in Google. So just try not to find things in Google. Just try to see things by yourself. Another assignment, I want you to study the same empirical mass formula. There's a very nice explanation in Crane. Crane chapter 1 is a mass read. And this is the same empirical mass formula, which actually explains nicely this trend of the binding energy curve. Not this up and down, but I think just reproduce the gross shape of the binding energy curve. And this symmetry energy term in particular, it gives you the slope, the negative slope coming after cobalt 62, which is the most tightly bound nucleus in the nuclear chart. So this symmetry energy, if you increase the symmetry energy, this slope comes down. I want you to investigate what is the same empirical mass formula, what is telling you. And again, I give you always a reference for you to have a look and read. We need to study more things about masses. We can determine what is the Q value of a reaction. This is actually quite important because as you know, in chemistry, actually, a nuclear reaction or chemistry, any reactions, if you have a positive Q value, they are called exothermic. If you have a negative Q value, they are called endothermic, which means that you need to provide energy for the reaction to happen. For a positive Q value, the reaction may happen spontaneously. So these are the keywords that I want you to remember. But basically, our goal is we take those table and the table of masses, we get the mass excess, we calculate what is the mass of the nucleus in particular, and then we can calculate anything we want. We can calculate what is the radius of the nucleus. We can determine what is the binding energy, or we can, there's a lot of things we can calculate once we know how to get from here to there, right? I want for here to here, for instance. So for that, we need to know the masses of nuclei are very important. Atomic masses are very important in nuclear physics. And I want you to be versatile and be able to calculate anything, always remembering these simple equations that we are introducing, these conversions. Actually, for this one in particular, I should also say that in the CGS system, E square is equal, actually E square over 4 pi epsilon, not 1.4 MeV Fermi. We also need that for, this is an E, and this is a square. All right. So these are the things that we need to move it away from here to solve this problem. The range of the nuclear force, this constant is also very important. And a given is the radius of the alpha particle. Okay, so with that, we finish for today. I don't want, again, to make these videos too long, because then there's a lot of memory involved, big size. We may have problems with our data. Okay, any questions? Before we go, I want you to ask me some questions.